Now, how that crushing takes place. So, which are the failure equations we are using in this design? So, in the design, we are always using the equation, or we are always using the stress equation wherever there is a chances of failure of the component. So, as far as SPIGOT is considered, when this cotter is inserted into the SPIGOT and socket point, and if it is subjected to tensile load, this cotter, when it is inserted here and it is available here in the assembly, this will try to come out of this slot, and when it is subjected to tensile load, it applies a crushing at the slot, crushing at the thickness of the slot. That means if we take disassemble it, if we try to imagine here, this cotter will try to come out of this slot, and due to that, when we apply tensile load, it applies a crushing. It will try to crush this slot. So the vice versa, right? This slot will try to crush the cotter, or cotter will try to crush the cotter. So what will be the area subjected to the crushing? The area subjected to crushing will be the area of the slot. So how will that cross section looks like which is subjected to crushing? This will be equivalent to the area under crushing. So this cotter will try to crush the slot, or slot will try to crush the cotter. So what is the area of that cotter, or area of the slot? So this cross section indicates the point where the failure will take place. So this having thickness D, this is having diameter D1, right? So this is having diameter D2, as we have already discussed. Diameter of this rod is D2. So hence crushing stress, we have discussed that. What is crushing stress? Applied force upon which area? Projected area. So bearing stress and crushing stress we have discussed. Whenever there is relative motion, and if the kind of compressive or kind of crushing is takes place into the component, that stress is called as bearing pressure. And if the crushing or kind of compressive stress is compressive failure takes place in the component, if there is no relative motion, the kind of stress developed in the component is called as crushing stress. Now hence, as sigma cr will be depends on the material of the component, and sigma cr is taken as equivalent to SYC, that is yield strength in compression divided by factor of safety. Understand? So what will be the yield strength of the component? How much is the value? It is available in the problem. So sigma CR is equal to SYC upon factor of safety. Available force, applied force will be given in the problem, and projected area will be equal to, so what will be the projected area of this component? D2 into T. Right? So again, from this equation, if T is known, we can find out D2, right? So the question will definitely arise. In earlier equation also we will get dimension D2. In this equation also we will get dimension D2. So why would there is a need to have two equations? Because the chances of failure of this COTTER joint at the place of the slot is two chances. One is crushing failure and one is tensile failure. Both are having equal chances of getting failure. Hence we have to find out the dimension for both the cases, and whichever dimension is more out of the two. So D2 in earlier case, that is for tensile failure, and D2 for crushing failure. Whichever D2 is maximum, we will select that is the final dimension for our design. So mark my words, if there is dimensions available by the two stress equations, we will consider the dimension which came maximum, right? Why we are doing this? Because if we select the maximum dimension, then whatever dimension which came minimum for the earlier stress equation, the particular diameter selected will be safer for that particular stress equation also. So remember my words, always select the maximum dimension which is available from the two stress equation or three stress equation, right? Then next one is shear failure. So if you see when crushing stress is increased, when crushing is increased, or when the component is subjected to tensile load and crushing is increased, then this cotter will try to cut this portion or shear of this portion and will come out. So if you see here, this portion is sheared off from the slot of the spigot rod because of the cotter and tensile load. So what will be the area of this crushing? So if you see this diagram, um, we have discussed here, if you see this assembly, in the assembly portion, this is area A, understand? And if this cotter shears off this portion of the spigot, individual spigot, if it comes out, that portion is A. Hence this distance is A, and what is the diameter? The diameter of this rod is equal to D2. So what is shear failure? Shear failure is failure due to which load? Two equal and opposite loads acting at through the center line. So this type of shear stress is called as direct shear. Direct shear is called as applied force upon cross-sectional area. So what is the cross-section? This is the cross-section. From this side also it is getting sheared off, from other side also it is getting sheared off. So it is equal to 2 into cross-sectional area. So what is this cross-section area? A, it is rectangular cross-section, A into D2. So this is equal to 2 into D2 into A. Now D2 from earlier equation is known, P will be available in the problem. Now shear stress is equal to SSY upon factor of safety. Now SSY, what does it mean by SSY? That is yield strength in shear for the material of the spigot. If steel is the material and SSY is taken as equal to 0.5 times of, most of the time it is equal to 0.5 times of SYT. So all the stresses SYC, SSY is founded out in terms of SYT, because SYT is the yield strength in tension for the available material. So if SYT is known and direct shear stress is SSY upon factor of safety, SSY will be taken as 0.5 times of SYT divided by factor of safety. So direct stress will be known, available force will be known, the crushing area, that is area of cross section in the shear, is 2 into D2 into A. So what is the unknown equation from this is A. From this equation we will get dimension A, right? So this is shear failure of the spigot. So after shear failure, let's have another failure. So this is crushing failure of spigot collar. Now if you consider a spigot collar, here this is called as an collar of the spigot, right? So up till now we have considered 4 equations. That 4 equations was, or the failure of that COTTER joint at the spigot was due to tensile load. But it is very easy to assume that, or it is very easy to understand that there are another chances of failure of this component. So mark my words, what word I am using, chances of failure. We have to design the component by assuming that what are the chances of failure. So when this component is subjected to tensile load, in case of spigot, there are 4 chances of failure due to spigot. What are that? First one, it will be failed at due to tensile load here, then tensile stress at the slot, then crushing at the slot, then shear of the slot. This is 4 due to tensile load. Now what are the chances of component to get failed when this tensile stress is released and it is subjected to compressive stress, right? So this portion of the collar will be subjected to compressive stress for the assembly. For the assembly means what? Let's consider here. Now this portion of the spigot collar have a chance to get failed by a compression. When tensile load is released, it will be subjected to compressive load. So this portion of the collar will be subjected to compression. So what are the chances of failure due to that compressive load? So first one, this collar of the socket will compress the collar of the spigot, and this compression will result in compressive or crushing failure of spigot collar. Now what is the area under crushing? So area will be this much area of the collar. So what is that area? So that area will be equal to let's assume here let's draw that area. So this is the external diameter of the collar, and this is the diameter of the another end of the rod of the spigot. So this diameter is equal to diameter D2, right? This is what diameter D2 we have discussed earlier. Then the outer diameter is, in this case, so if you see the diagram, this diameter is equal to D3. What is the diameter? D3. D3 diameter, external diameter of the collar. So this diameter is equal to D3, right? So what is the area under crushing due to the compressive load? This is the area that we have to find out. So crushing stress, what is the formula for crushing stress? Applied force divided by projected area. Which area? Mark my words, projected area. We always consider projected. Why it is called as crushing? Because when the compression takes place or the crushing stress, there is no relative motion between the two components, hence it is called as crushing stress. So crushing is equal to force, applied force upon projected area. So what will be the projected area? So let's change the color so that you can understand the meaning of that projected area. Now what is the projected area? If we take this area and if you project it, it looks like a circle. So projected area is equal to pi by 4, right? It's a circular cross section, multiply by d1 d3 square minus d2 square, right? So from this equation, as d2 is known from the earlier equation, only unknown quantity is d3, and sigma cr is equal to syc upon factor of safety for the spigot, for the material of the spigot. So syc will be available from the material, the applied force will be known, only unknown parameter from this equation is dimension d3. So by using the crushing equation, we get dimension d3, that is this dimension d3, that is diameter of the spigot collar. Then next, what is the shear failure of the spigot collar? Now shear failure of the spigot collar means what? Again, this is the spigot collar. When crushing takes place due to this socket collar on the spigot collar is increased, this portion, this particular portion will try to get shear off and removed from this. So there will be a ring like this. There will only remain a ring like this, right? So this much ring will be come out, and this will be subjective like this. This particular ring, right? Having some. So this is having, this ring is having diameter d3, right? It will come out of that rod of the spigot collar. So what is the area under shear? Area under shear will be the circumference of that ring. So if you consider this much collar will get sheared off when it is constantly subjected to compressive force. This will come out sheared off from the surface of the spigot rod having diameter d2, right? Having diameter d2. So right, so what will be the surface area or circumference of that? Now if you see, this is thickness T1. So what is the circumference of that which is subjected to the shear failure? The circumference, this circumference. So if you consider this rod, right, and if this is the portion where the this is the portion where the collar was available, so we have to consider this circumference, right? So how much is that circumference? So shear failure of spigot collar, which shear is this? Is again a direct shear, then applied force divided by the shear area. So how much is shear area? If the collar surface was available here, the circumference of that collar is equal to pi into pi into d2 into t1. So from this equation, d2 was available from earlier equation, only unknown is t1, applied force is known, direct shear stress is again equal to SSY upon factor of safety, which was known from earlier cases of shear. Again, SSY is equal to 0.5 times of SYT, where SYT is for the material of the spigot. So what is the material of the spigot? That depends on the applications, but generally the material used for this whole cotter joint is generally it is plain carbon steel of different specification. So we are going to have a separate session on material selection for the cotter joint and knuckle joint, right? So generally plain carbon steel is used. So for plain carbon steel, it is yield strength in shear that we are going to select, right? So from this equation we will get dimension, that is thickness T1 of the collar,